Hello, welcome to 3.5, Transformation of Functions. Transformations when we're going to be shifting things horizontally, vertically, or multiplying them by a leading coefficient that might make things narrower or wider. So first thing is horizontal shifting. Let f of x be a function whose graph is known, and let h be a fixed real number. If we replace x in the definition of f by x minus h, we obtain a new function, g of x equals f of x minus h. So we're modifying this part inside the function. We're modifying x before it's acted upon by f. And that's going to cause horizontal shifting. The graph of g is the same shape as the graph of f, but shifted to the right by h. And so h units if h is positive, and shifted to the left if h is negative. So if it's f of x minus 2, it's going to go to the right 2. If it's f of x plus 2, it'll go to the left 2, because think of it as x minus a negative 2. So compare the graphs of f of x equals x to the fifth, g of x equals x minus 3 to the fifth, and h of x equals x plus 2 to the fifth. So here's our original function. Here's that same function shifted to the right by 3. Right 3 units. And this one, think of this as h of x equals x minus negative 2 to the fifth. And that's the part that gets people. And this is shifted to the left 2. Now we'll talk about vertical shifting. I think this is a little more straightforward. Let f of x be a function whose graph is known. Let k be a fixed real number. The graph of the function g of x equals f of x plus k is the same as the original f, but shifted up if k is positive and down if k is negative. So I'm going to look at f of x equals x squared, g of x equals x squared plus 2, h of x equals x squared minus 4. So here's the original. This one shifted up 2 because it's a plus 2 down below. And this one shifted down 4. Oh, wrong button. Scroll down. Sorry about that. Reflecting with respect to the axes. Let f of x be a function whose graph is known. That sounds familiar now. The graph of the function g of x equals the negative of f of x is the reflection of the graph of f with respect to the x-axis. So like here's the original, f of x equals x squared, g of x equals negative x squared. It's reflected below the x-axis, across the x-axis. The graph of the function g of x equals, now watch this, the negative f of the negative of x. So the negative's inside here. It affects the x before it is applied to the function. Is a reflection of the graph of f with respect to the y-axis. It'll go across the y-axis. And we'll see that down here. Here's the original. This should have said, well, g of x would be the negative of x cubed. So that's why what was over here on the first quadrant, now in the second quadrant, what was in the third quadrant is in the fourth quadrant. It goes across the y-axis. So that's reflecting graphs. Now we have stretching and compressing graphs. Let f of x be a function whose graph is known. And let a be a positive real number. The graph of a function g of x equals a times f of x is stretched vertically compared to the graph of f if a is bigger than 1. So it'll stretch it vertically, pulls it vertically. The graph of the function g of x equals a times f of x is compressed, squished vertically compared to f if a is between 0 and 1. So here we have f of x equals absolute value of x, g of x equals 2x, 2 times the absolute value of x. So everything is higher up. Didn't label these graphs, but First one here is f of x. Here's g of x equals 2 times the absolute value of x. Everything's pulled up. And to think about that, so this would be like g of x is 2 times f of x. So that here, if it goes through 1, 1, this one's going through 1, 2. If it goes through 2, 2, this one's going through 2, 4. Everything's twice as high. Next one, f of x equals absolute value of x, g of x equals 1/5. So here our a is between 0 and 1, non-inclusive, so it's going to compress it. So if there's your original graph, for example, it went through 1, 1, here it goes through 1, 1/5. This one goes through 5, 5. This one's going to go through 5, 1. Let's go on to example 5. How will the graph of k of x equals the negative of the square root of x, then plus 2, compared to f of x equals the square root of x? So let's look at x, f of x. We'll go with 0, 1, 4. That's about as far as we can go. That's going to be 0, 1, and 2. Let's talk about the square root of x. Looking at this kind of a curve. But what's happening with the k of x? Change to red, I think it shows up better. So this negative here reflects across the y-axis. So it'll come over here. Then the plus 2 will shift it vertically. So 0 will still be 0, but then it's going to go up 2. 1, 1 will be negative 1, 1, but then it'll go up 2. 4, 2 will be negative 4, 2, but it'll go up 2. So we get this kind of a curve. Okay, so k of x resembles f of x, except it is shifted vertically by 2, and it's reflected across the y-axis. Let's go on to our next one. Next concept is y-axis symmetry. The graph of a function f has y-axis symmetry, or symmetric with respect to the y-axis if f of negative x is f of x for all x in the domain. Such functions are called even functions. That's really important, even functions. So even functions have y-axis symmetry. F of x equals x squared is an even function. F of x equals x to the fourth is an even function. Origin symmetry, the graph of a function f has origin symmetry, or symmetric with respect to the origin, if f of negative x is the negative of f of x for all x in the domain of f. Such functions are called odd functions. So odd functions have origin symmetry. And f of x equals x cubed is an example of that. It has origin symmetry. So this is reflected across the origin up to that. Whereas up here, that's not a very good drawing. This is mirrored across the y-axis. Symmetry of equations. We say an equation in x and y is symmetric with respect to the y-axis if replacing x with negative x results in an equivalent equation. Symmetric with respect to the x-axis if replacing y with negative y results in an equivalent equation. And the origin if you replace x with negative x and y with negative y results in an equivalent equation. So determine if the function is even, odd, or neither, and the graph of the function. Determine if the equation has y-axis, x-axis, y-axis symmetry, x-axis symmetry, or origin symmetry, or none. So we have h of x equals x cubed minus 1. If we look at f of x equals x cubed, that would be like this. Now that has origin symmetry. But I'm trying to talk about this h of x. So h of x is f of x, but it's shifted down one vertically. So it's going to go here, there, there, and there. So let's look at h of negative x. That's going to be negative x cubed minus 1, which is negative x cubed minus 1. That's not the same as the original. That's not the opposite of the original, so it's neither even or odd. I should say nor odd. Nor, okay. As far as symmetry goes, h of negative x is not equal to h of x, so no y-axis symmetry. The negative of h of x is not going to be equal to h of x, so no x-axis symmetry, and excuse me, the negative of h of negative x is not going to be equal to h of x. So no origin symmetry. Okay, so it has no symmetry. Let's go on to our last page here. We have another example like this to do. Feel free to pause. X equals the negative of y squared. So if we're to graph this, let's go ahead and graph this. Now y is the independent variable in this case. So we'll go with like negative 2, negative 1, 0, 1, and 2. So we have the negative of y squared, that's going to be negative 4, negative 1, 0, negative 1, negative 4. So then 0, 0, negative 1 is both 1 and negative 1. And then we have negative 4 is both 2 and negative 2. So we can see right off it's not going to be a function. So let's try it. Is it even? The negative of x equals negative y squared. That means x equals y squared. So it's not the same as original. So it's not even. And that means it has no x-axis symmetry. Or sorry, no y-axis symmetry. we do for odd, x equals the negative of negative y squared, x equals negative y squared. So that means this is the same as the original, same as original. So it has x-axis symmetry. And if we do negative x equals the negative of y, negative y squared, that's negative x equals negative y squared, x equals y squared, not the same. So it does, there's no origin symmetry. Okay. So it does have, it is odd with x-axis symmetry. Okay, monotone, intervals on which the function is increasing or decreasing. If it's going up, 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 it's monotone. If it's going down, 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 it's monotone. If it's going up and down, that's not monotone. In the same interval. Increasing, decreasing, and constant. I'm going to either scroll this up. So pause if you need a pause for the material above. Let's say the function f is increasing on the interval for any x1 and x2 in the interval, with x1 less than x2 if f of x1 is less than f of x2. So if the two x's, one smaller than the other, the smaller one has to have the smaller f. That means it's going up. It's decreasing if for x1 and x2, x1 being less than x2, f of x1 is bigger than f of x2, that means it's going down. Constant if for x1, x2, f of x1 equals f of x2. It's constant. So find the intervals for which the function is increasing, decreasing, or constant. So if we think about f of x being absolute value of x, it's going to be this. What we have here, g of x is going to be, which is negative absolute value of x minus 2. It's going to be shifted right and reflected across the x-axis because of the negative. So instead of going like that, it's coming down and going to the right. This is increasing. It's going up. Going up, 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 up to that point. So from 0 to 2, no, negative infinity to 2, it's going up. And then it's decreasing, means it's going down from 2, x being 2 to infinity. At 2, it's neither increasing nor decreasing. Okay. That'll do it for 3.5, transformation of functions. I hope you enjoyed that. I hope that was informative. Thank you. Send me your questions.